In this new era of AI, our data can be our single greatest liability, opening us up to lawsuits, fines, and total product failure.
We live in a world that absolutely runs on data. Everything from our hospitals to our financial systems relies on it. But that brings up a huge question, maybe the most critical one of our time. How do we actually know the data is telling the truth? Well, let's dive in.
So let me just ask you this straight up. Can you trust an algorithm with your life? Because, more and more, that's exactly what we're being asked to do.
And here's why. That question isn't just some far-off thought experiment. It turns out that in medical diagnostics, some AIs are learning a really dangerous shortcut. Instead of spotting diseases, they're just getting good at identifying which specific MRI machine took the picture. Not the cancer, the machine. Happening right now in labs and hospitals. Places where the stakes could not possibly be higher. So what on earth do we do about it? It really all starts with understanding this clever little trick the AI is pulling, this dangerous shortcut, and figuring out how to build a system that basically forces it to learn the right lessons. The solution, it turns out, is to give our data a kind of pedigree, a detailed history that tells us exactly where it's been, what's happened to it along the way. We have to be able to track its digital fingerprint. And the first key idea here is something called provenance. The easiest way to think about it? It's the data's birth certificate. It tells you its whole origin story, who collected it, what machine it came from, in which hospital, on what date. Without this, there's no way to know if the AI is cheating the system. Okay, so building on that, the next piece of this puzzle is lineage. If provenance is the birth certificate, then lineage is the data's entire life story. It's this detailed log of every single change, every calculation, every system it's ever passed through. Together, these two things create a complete, unbroken audit trail. But here's the thing, the level of detail really, really matters. With what's called coarse-grained provenance, you might just know that 1,000 images came from Hospital X. But with fine-grained provenance, you know the specific machine, the exact time, and the operator for every single image. And that is the level of detail you need to catch an AI that's trying to take a shortcut. This all leads to this just brilliant idea, the dataset nutrition label. Just imagine, before you feed any data to an AI, you could look at this label and see all of its ingredients, where it came from, any potential biases, its entire history. It's all about total and complete transparency. Now, this kind of detail isn't free. It comes at a cost. Implementing this super detailed, fine-grained tracking can actually slow down a system's processing speed by as much as 24%. So you've got this critical trade-off. But in high-stakes fields like medicine, the choice is becoming obvious. Giving up a little speed to guarantee your data is trustworthy? That's not a cost. It's an absolutely essential investment. Okay, so we've tracked our data's history. We know where it's from, but what about the data itself? We have to make sure the measurements are fundamentally sound. And this brings us to two of the most important and often confused concepts in all of science: accuracy and precision. They sound kind of similar, right? But they are critically different. Accuracy is all about how close a measurement is to the true, actual value. Precision, on the other hand, is about consistency. If you measure the same thing over and over again, how close are your results to each other? And here is the absolute perfect way to get the difference. Imagine a thermometer that always reads 1 degree too high. It's incredibly precise, right? It gives you the same wrong answer every single time. But it's not accurate at all. For data to be trustworthy, it has to be both. All right, so we've got the principles down, but how in the world do we apply them at the massive scale of modern technology? Well, that's where an entire arsenal of data tools comes into play. To really enforce this stuff at scale, modern data pipelines are basically built like an assembly line for trust. Data gets inspected at every single stage, when it comes in, while it's being processed, and right before it's stored. Nothing gets through without passing these quality checkpoints. And to run these checkpoints, engineers have this whole suite of specialized tools. And there's really no single best one. For messy, unpredictable data that kind of needs a human eye, a tool like OpenRefine is perfect. But if you need to validate millions of records against a super strict set of rules, you need the automated power of something like Great Expectations or Pandas. It's all about using the right tool for the right job. And to handle these massive data sets, the validation just has to be automated. So programmers use frameworks like Pydantic and Pandera to set rules right inside the code. For instance, a rule that says an age value must always be a positive number. If any data breaks that rule, it gets flagged or just filtered out automatically. And this idea, it extends from the very lowest level of programming all the way up to the tools that researchers themselves are using. From one little line of code that rejects a negative age, all the way up to a huge clinical research platform like REDCap that stops a scientist from accidentally entering a patient's weight as 2,000 pounds. This idea of integrity is built into every single layer. So why go through all this trouble? Well, because without it, data engineers can spend up to 40% of their time just cleaning up manual data entry errors. So automation isn't just about trust, it's about efficiency. It frees up brilliant people to go solve much bigger problems. But even if you have perfectly clean, perfectly tracked data, there is one final, kind of profound concept we have to talk about: uncertainty. It turns out there are two kinds of uncertainty. The first is aleatory uncertainty. This is just the inherent, unavoidable randomness of the universe. Think about rolling a die. You can't reduce that chaos. But the other kind, epistemic uncertainty, that comes from a lack of knowledge. It's the uncertainty we can reduce by getting more data or building better models, and knowing which is key. To manage all this, scientists actually use a global standard called the GUM framework. It's really just a 4-step process for identifying, measuring, and combining all the different sources of error. The main takeaway is simple, but it's really profound. A trustworthy result isn't just a number, it's a number that comes with a known level of confidence. And that brings us right back to where we started. The ultimate goal of all of this, the provenance, the precision, the tools, the uncertainty budgets, it's all about building trust. So as our AI systems get exponentially smarter, the real question we're left with is this: how are we going to continue to design systems that make sure they stay honest?
All right, let's talk about data integrity. But first, I want you to stop thinking about it as some back-office IT issue. I want you to see it for what it truly is: our single most important risk mitigation strategy. It's how we protect this company, it's how we protect our investments, and it's how we make sure our most exciting innovations don't completely fall apart.
So let's start with what is, quite literally, a multi-million-dollar question. We spend fortunes developing these brilliant medical AI models. We get them right to the 1-yard line, and then they fail. And I mean, they fail spectacularly. Why does this keep happening?
Well, the brutal truth is that it's usually not the algorithm's fault. The failure is almost always buried deep in the data itself. You see, if the foundation is flawed, if it's poisoned from the start with bad, inconsistent, or unreliable data, then even the smartest AI on the planet is going to produce catastrophic results. We're talking product recalls, huge regulatory fines, and a complete loss of trust in the market.
To prevent this, our strategy is built on two very solid pillars. First, there's clinical compliance. Think of this as our legal armor. It ensures every piece of data we have can withstand the toughest scrutiny. And second, we have metrological precision. This makes sure our data isn't just legally defensible, but that it's scientifically correct. Let's start with compliance.
Okay, so pillar number 1, compliance. This is our foundation. It's the framework of rules that guarantees every single data point we generate, every record we keep, can hold up under a microscope, especially when that microscope is being held by the FDA.
And in our world, the gold standard for this is a framework called ALCOA. And let's be crystal clear, this is not a suggestion. It's a non-negotiable set of principles for anyone managing clinical data. If you don't master ALCOA, you don't have compliance. It's that simple.
ALCOA is an acronym, of course, and it stands for 5 principles that basically seal every potential loophole in your data. Think of it as 5 questions our data must be able to answer. Is it attributable? We need to know who did what and exactly when. Is it legible? Can we actually read it even years from now? Is it contemporaneous? Meaning, was it recorded right when it happened, not from memory hours later? Is it the original record? And finally, is it accurate? Does it reflect what really happened in the real world? You get these 5 right, your data is basically bulletproof.
But, we live in a digital world, so ALCOA had to evolve. It grew a plus sign. We now talk about ALCOA Plus. That plus is so important. It covers electronic records and adds things like making sure the data is complete, consistent, and always available. But the big one is secure access controls. In an age of copy and paste and hitting the delete key, we have to prove, without a shadow of a doubt,
Who touched the data and when?
And this is where the rubber really meets the road. The FDA's regulation, 21 CFR Part 11, makes this the law. It demands a perfect, unforgeable audit trail. If any data point is ever changed for any reason, you absolutely must document 4 things: what the original value was, what the new value is, why you changed it, and a digital signature and timestamp from the person who made the change. There's no wiggle room here. No ambiguity is allowed.
Okay, so let's move on to our second pillar. This is where we go beyond just following the rules and start talking about scientific truth. Because look, having a perfect audit trail is great, but it's totally meaningless if the data you're recording is garbage to begin with.
And this brings us to a much deeper, more fundamental question. Forget the audit trail for a second. Can we actually trust the numbers coming out of our devices? Do they reflect reality? This is the science of metrology, the science of measurement itself.
Now, this slide highlights something that trips people up all the time: the critical difference between accuracy and precision. Just look at the targets. Accuracy is about hitting the bullseye. Are you close to the true value? Precision, on the other hand, is all about consistency. Are your shots tightly grouped together, even if they're all way off in the corner? You can have one without the other, and that's exactly where the danger is.
And this is where things get really risky. Imagine a device where the readings are scattered all over the place. The average of all those shots might be right on the bullseye, so you could argue it's accurate on average. But any single reading is completely unreliable. And for a critical clinical decision where one single data point can change everything, that kind of data isn't just worthless, it's incredibly dangerous.
So understanding that difference between accuracy and precision is absolutely key. Because once you get it, you can start to diagnose and control the 2 main types of error that can corrupt our data and sink our products.
So what are they? First, you've got systematic error. The classic example is a miscalibrated scale that always tells you you're 5 pounds heavier than you are. It's a consistent, repeatable bias that pulls all of your results off target. This is what kills your accuracy. Then, on the other side, you have random error. Think of this as unpredictable static or noise in the system. It doesn't push your data in one direction, it just scatters it around. This is what destroys your precision.
This table is really our playbook for getting this right. It shows us exactly how to take control. We fix accuracy by hunting down and eliminating those systematic errors, like recalibrating that scale. We improve precision by reducing random noise. And then we have to worry about 2 other things: resolution, what's the smallest change our instrument can even detect, and tolerance. What's the acceptable level of variation in our manufacturing process? Each metric gives us a specific lever we can pull. So we've got the rules of compliance down, and we understand the science of precision. The final challenge, the big one, is how do we actually do this? How do we apply this incredible level of rigor automatically across millions of data points, all the way from the lab bench to the cloud? The whole goal here is to create a totally unbroken chain of trust. We have to build a seamless bridge from the physical world of instruments and sensors to the digital world of our databases and AI, making sure that the integrity we establish at the very beginning is never, ever lost. Look, you can't do this with spreadsheets and elbow grease. It's impossible. We use modern computational tools to automate the whole process. And the key idea is actually pretty simple. Instead of just tracking a number, like 10.0, the software tracks the number plus its known uncertainty. Think of it as 10.0, give or take 0.5. Then, as that data moves through our systems, the software automatically calculates how that little cloud of uncertainty grows or shrinks with every single step. What's so powerful about this is that it lets us mathematically separate 2 different kinds of uncertainty. There's the inherent randomness in the universe that we just can't get rid of. And then there's the uncertainty that comes from gaps in our own knowledge. The result? We don't just know what our data says. We know exactly how confident we should be in that data. And that is a massive strategic advantage. And that leaves us with one final thought. In this new era of AI, our data can be our single greatest liability, opening us up to lawsuits, fines, and total product failure. Or, with a rigorous 2-pillar strategy like this, marrying compliance with precision, it can become our most powerful, most defensible, and most valuable asset, the true engine of our innovation. The systems we build today will determine which of those futures we get.